Stress is defined as the force or system of forces that are applied to a certain cross-sectional area that tends to deform a body. To calculate it, use the equation stress equals force divided by cross-sectional area. There are multiple types of stress, including tensile, compressive, shear, bending, and torsional. Tensile stress occurs when forces pulling on an object cause it to elongate. Compressive stress occurs when a force applied makes the object compress. Shear stress occurs when two forces opposite in direction are applied tangentially to an object but do not cancel out. Bending stress occurs when only one force is applied to the middle of an object while the ends are fixed. Torsion stress occurs when an object is twisted axially. Strain is the response of a system when stress is applied. It is the amount of deformation the object experiences after the stress is applied. It can be calculated using the equation strain equals change in length divided by the original length. The different types of strain correspond with different types of stress. So tensile stress results in tensile strain, compressive stress pairs with compressive strain, shear stress results in shear strain, bending stress causes bending strain, and torsional stress results in torsional strain.
Typically, the greater the stress, the greater the strain. The proportionality constant between the two is called the elastic modulus, which is different for every material. The elastic modulus is a combination of different constants that correspond with the different types of stress and strain. The most well-known elastic modulus is Young's modulus, that is associated with tensile stress and strain. It can be calculated using the equation Young's modulus is equal to tensile stress divided by tensile strain. A material that is more resistant to elastic or recoverable deformation has a higher Young's modulus. In addition, the modulus that is associated with compressive or bulk stress and strain is known as the bulk modulus. It is a measure of the ability of a solid object to resist changes in volume when being compressed from all sides. It can be calculated using the formula bulk modulus is equal to bulk stress divided by bulk strain. This means a material that is hard to compress has a high bulk modulus but a low compressibility, and a material that is easy to compress has a low bulk modulus but a high compressibility. The elastic modulus that corresponds with shear stress and strain is referred to as the shear modulus, which measures the ability of a material to resist transverse deformations and is only a valid indication for small deformations, after which the material is able to return to its original form. Because materials with larger transverse deformations lead to permanent fracture, it cannot be measured using the shear modulus. The shear modulus can be calculated using the equation shear modulus is equal to shear stress divided by shear strain. It is an indication of a material's rigidity. Therefore, a material that is more solid and rigid will have a higher shear modulus than a material that is flexible. Furthermore, the elastic modulus that corresponds to bending stress and strain is known as the flexural modulus. It is a measurement that denotes the ability of a material to bend. It can be calculated using the equation flexural modulus is equal to bending stress divided by bending strain. It is only accurate on materials that do not break or fracture upon applied stress. Finally, the elastic modulus associated with torsional stress and strain is approximately equal to the previously discussed flexural modulus.
The concept of Young's modulus is extremely important, especially in regards to the materials that are used in the construction of buildings and roadways. When constructing a building, one must first take into consideration what types of stress will be present. For example, say a roof was constructed using a truss. Within this truss, 4 of the 5 forces previously discussed occur naturally, which keep the system at equilibrium and prevent it from collapsing. These forces being tension, compression, shear, and bending. Torsion is not present in this system. Bending force from gravity occurs on the top beam due to its long length. To counteract this force, another beam is placed underneath it so it bisects the top beam at a 90-degree angle, causing most or all of the bending force to be transferred into the middle beam, which then gets compressed. This compression causes a shear force in the bottom beam, which occurs right at the point of intersection with the middle beam. To counteract this shear force, another angled beam can be placed towards the middle of the truss to cause a tension force in the bottom beam and to redirect the shear force to the apex of the truss, where it is cancelled out by the shear force caused by the beam of the opposite side of the truss. When constructing a truss, architects must also consider what type of materials can be used to best counteract the forces present. Materials can be classified into 3 different groups: metals, ceramics, and polymers. Metals are metallic elements and alloys of those elements, including aluminum, copper, and steel. Due to their crystalline structure, ductility, and malleability, metals are easily formed into specific shapes used in architecture. Ceramics are non-metallic oxides, nitrides, or carbides of different elements. For example, tungsten carbide, boron carbide, and silicon dioxide are all ceramics. Ceramics are typically hard, very brittle, and have good wear properties. Polymers are natural or synthetic long-chain molecules made up of repeating units, or monomers. Polymers also include materials such as nylon, Kevlar, and cellulose. These materials are typically flexible, typically have lower melting points than metals or ceramics, and are very strong for their weight. Keeping this information in mind, we can now decide what materials are best placed in the truss previously analyzed. Because metals handle tension very well due to their strength and ductility, a metal or an alloy would be best placed in the bottom beam of the truss. Polymers handle bending force very well due to their high flexibility without breaking, so a polymer such as wood should be placed in the top beam. Finally, ceramics handle compression well due to their high density and rigid crystal structure, so a light ceramic such as silicon carbide should be used in one or more of the middle beams in the truss.
Torsion is a special case because it does not often occur in stable structures. However, the way a material reacts to torsional stress is important when considering a material for an axle or another rotating object. Torsion stress is very similar to bending stress, except torsion occurs about an axis while bending occurs tangential to a plane. Therefore, a material that handles bending stress well will likely also handle torsion well. The shape of an object that undergoes torsion also has a great effect on whether or not the object will resist the stress. For example, an I-beam's unique shape allows it to resist bending force easily because the web prevents the 2 phalanges from stretching too far on the bottom and becoming too compressed on the top. However, when an I-beam undergoes torsion, nothing stops the web and phalanges from being twisted around the axis of rotation, so the shape is not ideal for handling torsion stress. A cylindrical pipe or rod, on the other hand, would resist torsion very well. This is because the force is being applied evenly around the edge of the object, which resists the compressive force of the edges being forced towards the center of the rod.
In conclusion, there are 5 different types of stresses that can be exerted on objects: tensile, compressive, torsional, bending, and shear. There are also 3 different types of materials that are commonly used: metals, ceramics, and polymers. Different materials will resist different types of forces to a greater or lesser degree based on their mechanical properties. Shape also plays into how different objects react to different types of stress. These properties can be used to determine which materials are best placed in a structure or architectural creation.